hit my record and blow this up a little bit. Did we do 22? That looks familiar.
No,
we
did not.
Okay. Let's do it then. Go ahead. I'll give you a shot at it first.
Okie dokie. Angle CAB equal to 68 degrees. Find angle 1. So we know that they're bisected. So if the whole angle is 68 degrees, angle 1 would have to be 34.
Yeah. For some reason, it's covered up.
Yeah.
The fact that that's the angle. There it is. It says the angle bisector at the top.
Yeah. So that means it's divided by 2.
Okay. That's a pretty easy one. How about number 23? Here, let me blow this up just a little bit so I can draw on it. I can label some of these angles.
Okie dokie. So
angle 2 is that one, 12x plus 3. And angle QSR, in other words, angle 1 and 2, that's 1 and 2, and that's angle 2 only. So how do you solve for x?
12x plus 3 plus 12x plus 3 equals 27x minus 3.
Okay, be careful. QSR is this angle right here. So oh, that's an angle bisector.
Yes, they're both.
Yeah, I forgot. I have it covered up on my end. I'm not looking at it. And I'm sitting here trying to figure out how we're going to solve this because we can't. But if we know it's an angle bisector, then, yeah, what can we say? We can actually, there's an easier way to do it. 12x plus 3 equals 1/2 of everything else, right? I think that's the clearest way that makes sense to me.
Okay.
And you know how to solve that?
Just fine.
Let's go through the solution. First step.
Half of 27.
You know what? There's a better first step, isn't there? That's what I was going to do, was have you distribute the half. What's a better way to get rid of that 2 or that 1/2?
Multiply both by 2.
Yeah, and the reason that's a better way is because you don't have fractions. If I distribute that 1/2, I'm going to have 13.5x, and then I'm going to have 3 halves. I'm going to have 2 different fractions. Whereas if I multiply both sides by 2, I get 24x plus 6 equals 27x minus 3. Now no fractions. X equals 3. So that's kind of a good lesson. In other words, I usually have a standard rule on equations that you get rid of parentheses and denominators first. And so my tendency would be to distribute automatically, but it doesn't get rid of the denominator. Whereas if you multiply both sides by 2, you get rid of that denominator and the parentheses at the same time. Scroll down again. Okay, what equation am I going to write here?
Well, we know that a triangle is 180 degrees.
Okay.
So we do 9x minus 10 plus 40 plus 60 equals 180.
I'll take a shortcut and write it like that.
Because 40 plus 60 equals 100.
Right. So x equals 9. Excuse me, not 90, 9.
I think it would equal 10. Oh.
No, you're right. You're absolutely right. Especially since I don't see 9 over there on the answer, I quickly
realized that's why
I must have made a mistake. See what happens when you skip steps?
Yeah. I was just looking at the bottom. I was like, there's no 9.
No, there isn't. And it's not minus 9. I couldn't figure out what I'd done. What I'd done is skipped a step and made a math error because of it. All right. We can only hope that your test is going to have problems this easy. I'm a little surprised because this is honors geometry, isn't it?
Yeah.
Yeah. Maybe they'll get harder as we go on, but I think we're fairly near the end of this set of review material.
Yeah, we only have like one more page.
Yeah. Each figure shows a triangle with one or more of its medians. Some of these lines that cross this big outside triangle are both medians. What's a median mean?
Half. So like it's in the middle.
That can mean a couple different things. It means it bisects the opposite, it splits the line. In other words, that is equal to that. Those angles are not equal. And this is equal to that. Okay? By definition of a median. In other words, a median goes from a vertex to the middle of the opposite line. And find HF. HF equals 5x plus 3.
Yes.
And HJ equals 3x minus 3. So let's solve it the same way we did the last one. Same type equation. So what can I say?
You can do 6x minus 6.
Where are you getting the 6x? You mean 5x? In other words, what do I know? I know that that is half of that, right? So let's state it like that. That's the simplest way. So the short segment is half of the long segment. So how do I write that?
Short segment. So 3x minus 3 equals half 5x plus 3?
Yeah. Same exact way we did the last one. Now, what's the best first step?
Get rid of the denominator.
Okay.
So it'd be 10x.
Not 10x. You're not going to distribute it. You're going to get rid of it by multiplying both sides by 2. In other words, this is what I'm doing. And then that 2 will cancel with that 2, and you'll be left on the right side with something very simple. Again, no fractions. Now I get x equal 9. Again, not an answer. Actually, what's the question? Because it's not visible on my page.
Find HF.
Find HX. Oh, HF.
Yeah.
So if x is equal to 9, then we have 45 plus 3. Okay.
So that would be C.
Yeah. All right. And this is the last on that page. Okay, so we're looking for a 26. And that is the last page, isn't it?
Mm-hmm.
But that's okay. We got some tougher looking problems on this one.
Mm-hmm.
Well, I take that back.
Never mind.
It's not tough yet. So which angles have to be 90 degrees? Give them by letters. Whoops.
ACE.
Just a second. ACE?
Mm-hmm.
Okay, yeah. ACE, in other words, that one. Okay.
ACD.
Okay. That one.
And then there's also ACB.
Uh-huh.
And ACE again.
Well, I think there's only 3 of them, aren't there? Oh,
yeah, but
which 2 angles must be 90 degrees?
Mm-hmm.
Wow, I guess they're giving you your choice. Because there's 3 of them, clearly.
Mm-hmm.
Right? In other words, if ACD is 90, so is ACB by definition, almost. And then, of course, it's perpendicular to the whole plane. So it doesn't matter how you drew lines there. You could draw them any which way, and they'd be perpendicular to all of them.
Mm-hmm.
So I'm a little curious as to why they said which 2 angles must be 90 degrees. You know why they didn't? I wonder what their answer is. You suppose it's ACD and ACB? Because clearly ACE is also 90 degrees.
Mm-hmm.
Well, maybe they're just... Okay, second one. How many planes could be made from 10 points in space?
Well, 3 points make a plane.
Right. So a minimum, you have to have 3 points that aren't in a row, that aren't on a line. So that would make that plane M. How many planes could be made from 10 points in space? Well, if you had 3, I think only 3, right? In other words, you can have 4 points that make up one plane. But if you need at least 3 points to make a plane, you're going to have 3 planes with 1 point left over, and that doesn't make a plane, so that 1 point has to go in one of those other 3 planes, I believe. Unless I'm missing something. This is, I don't know. You agree or you feel different?
It's usually like a lot, like over 100, like for these types of questions.
Really?
Yeah.
There's one plane. If I draw a parallel plane to it, there's another plane. And if I connect up that, there's a third plane. And then there's a 4th plane. So that's 1, 2, 3, 4. And all of my points have to be on those surfaces. Can't have any points. I suppose I could make up planes in between inside the box, like a diagonal. But I don't see how that helps. Maybe. Okay, let's look at something. What if I have a plane there? or a point there, and I have a point there, and I'm looking at plane number 1 right now.
Mm-hmm.
And then if I look at plane number 3 and use that same points, so I can have some points in common here. So
Yeah.
you're right. I don't think it is 3. I think it's probably 4. Let's see. If I put the best point I could put would be that. And now I still have a plane number 1. And let's erase one of these. I tell you what's going to happen is I know where some of my points are going to go at the vertices. To be most efficient, there is 4 points that determine 1 plane. Okay? Here, let's make this read 3 like I meant, so you'll know what I'm talking about. Now, let's see. If I put 4 more points there, I've just determined 4 planes with 8 points.
Mm-hmm.
And now, if I put a diagonal plane in there, that is also determined. So I actually have 5 planes using only 8 points.
Mm-hmm.
And I can get another plane, which is kind of a set of diagonals. And so I have 6 planes using 8 points.
Mm-hmm.
And the other 2 points, I could put, I could put one like a triangle right there. There's another plane. I could tilt that. So that's plane number 5. No, I've already got a 5 and a 6. And I could put one more there. So I can get at least 8.
Mm-hmm.
And I'm beginning to think that I can probably get 10. In other words, there is probably a mathematical formula that I'm not aware of where you can get as many planes as you have points. Now, you might be right. It might be a 10 squared or something. Although I don't know. You have to have at least 3 for one of the planes. So it might always be 2 less planes than you have points. In other words, if you start with 3, let's say I start with 3 points at the vertices of that plane, and now I should be able to build, well, I've already seen that I can get 8 planes with 10 points. I'm not sure you can get 10. I really don't know. I'm kind of guessing, speculating here. I have no clue. And it's hard. This is one of those problems that's hard because it's hard to draw it because you're kind of looking in 3 dimensions. It's a little bit like some of those problems we did on a couple of your sessions where I used playing cards and stuff. That it was all about 3-dimensional geometry and planes and space and skew lines and all of that stuff. That tends to be some of the more difficult stuff in geometry. The 3D solid geometry, that's not so tough. But when you're talking about lines and planes and points, that tends to be tough. I'm going to guess 8. Wouldn't be surprised if it's 10. Wouldn't even be surprised if it's a lot more than 10, although I can't picture how it's going to be more than 10. In other words, the way I've drawn it over here This dot right there is part of 1, 2, 3, 4, 5 planes. One dot is part of 5 planes. So perhaps
Maybe
we can get 50 planes from 10 points. I don't know. Let's go on. Unless you have some other stuff to add to that. The other comment was actually pretty helpful. It certainly wasn't 3 planes. I think the key is making sure that these dots are on the vertexes of these planes, at least if you make the planes like rectangular or square.
Yep.
Use the following information. Let me scroll down. Okay. So on probability, basically the probability is defined as the number of successes divided by the total number of possibilities.
Yes. So
what's the total possibilities?
There's 14 animals, like, in total.
Okay.
And then
keep going.
there are 2 elephants and 2 zebras, so it would be 2 14ths plus 2 14ths equals 4 14ths, which is 2 7ths.
Okay. It's the probability of selecting a lion and then a hippo if you do not replace the first selection.
So it would be 3 14ths.
Hold on. What's a lion? 3. Okay. 3 14ths. That's the probability of getting a lion, which you have to do. And then a hippo. So what am I doing? Am I adding or multiplying?
Multiplying, because
both have to happen.
Yeah.
Okay. And so
then since you,
what's the hippo?
7 out of 13, because you took away.
Right. You already took away a lion.
Yeah.
So you get. Now, the way to do this is not 21 over that. It's to simplify first. Then you don't need a calculator. And you end up with 3 over 26.
That just makes it easier.
Yeah. Anytime you can not have to pull up your calculator. Anytime you can keep your numbers smaller, do it. And a lot of times in an awful lot of multiplications, when fractions are involved, you can always simplify those fractions before doing the multiplication. Okay. 30. The lottery uses the numbers 1 through 49, with 5 numbers being drawn to determine the winning ticket. How many possible outcomes are there in this lottery? All right. This is one that it's a counting problem, but it's too many to count. So you have to do it using combinations or permutations. Okay. So how many possible outcomes are there in this lottery? Now let's just examine one possible outcome. 1, 2, 3, 4, 5. Okay. Now, is that the same as 5, 4, 3, 2, 1?
No.
I don't know if it is or not, to be honest with you.
Well, it's different in the, like, real lottery.
In the real lottery, order matters?
Yeah.
Okay. If order matters, it's a permutation problem. If order doesn't matter, in other words, if that was the winning ticket or any ticket that had the numbers 1 through 5 in any order, that'd be a combination problem. But this is a permutation problem. Remember, and the biggest difference is if order matters, it's permutation. If order doesn't matter, it's combination. Do you play poker?
Not really.
So, do you know what a flush is? 5 cards of one suit. Okay?
Yeah.
Let's say you had the ace. If you had the ace of hearts, 8 of hearts, 7 of hearts, 6 of hearts, 5 of hearts, you would have a flush. But it doesn't matter the order. You could also have exactly the same flush if you had this, as long as they're all hearts. In other words, when you're playing poker, the order of the cards doesn't matter that you pick up. You pick up 5 cards, but you shuffle them around and it's the same hand. So order doesn't matter here, but certainly in the lottery, I think it does, because the winning tickets are always in a certain order. It's not just having the numbers, it's having them in the order they pick them, correct?
Yes.
Okay. So there is a fundamental equation that let's talk about. In pick R, which means it's a permutation. These are the total number of possibilities, and in this case, we're going to want 49, pick 5.
So
Now, this thing means, do you know what it means? Do you know the formula?
I think it means 49 times 48 times.
Yeah, it's n factorial all over n minus r factorial. Okay. And n factorial does indeed mean, so n is 49. So what we really have here is 49, pick 5. If it was a combination problem, we'd have 49, choose 5. It would be a C instead of a P. And the formula is a little different for combination problems. There's another r factorial in the denominator. But for permutation problems, it's just this. So it's 49 factorial divided by 44 factorial. Okay. Now, do you know how to simplify that?
Just figure out the factorials, then divide.
Well, you know what 49 factorial means, right?
Mm-hmm.
And you know what 44 factorial means.
Yes.
So I can simplify this by canceling the 44 down from the numerator. So my answer is going to be 49 times 48 times 47 times 46 times 45. Whatever that number is. And do you have a calculator that'll do factorial?
Yes.
Well, you could do 49 factorial divided by 44 factorial, or you could just multiply those 5 numbers out. It's good to know how to simplify these factorials, because a lot of times you'll be able to do them. A lot of times, like if we had 49 factorial over 47 factorial, then that would just be 49 times 48. I could do it real simple without having to use the factorial function.
Mm-hmm.
That's a pretty big number.
Yeah.
I don't know whether it's what? Like 47 to the 5th power. Anyway, that should be your answer.
Yeah.
I'll let you do the arithmetic. Okay?
Mm-hmm.
Let's go on to the next one, see if we can get this one covered. There are 13 sailboats in a race. How many different ways could the sailboats finish 1, 2, and 3?
That's a permutation, right? Because order matters.
Order does matter. This one, I can almost do... Well, let's see if we can do it both ways. Let's talk about it as a counting problem first, because all probability and permutations and combinations come down to counting problems. It's just sometimes there's so many that you can't do it. It takes too long to count them all up, and you need to use one of those formulas. However, in this case, if I were to label the sailboats A through whatever the 13th letter in the alphabet is, how many boats can come in first place?
13.
How many boats can come in second place after the first come in first place? And
12.
There's 11. And that should be the answer. You have answers on that?
No, I wish.
Okay, now let's see if we can come up with that number by doing it as a permutation. Well, what is that? Is that 13p3?
Yes.
Which would be 13 factorial over 10 factorial, which would be that. 13 times 12 times 11. In other words, you just cancel everything below 10 factorial out of the numerator.
And it's 1,716.
Okay. Again, the arithmetic I will leave up to you. Okay. That's the last one I have.
Yes.
That was the last page, right?
Yeah. Could that also be for number 27, combination?
Oh, did I leave one out? Did I not?
No. For how many planes could be named?
Oh boy. I don't know.
So
that to me is a problem that I don't know. Maybe you might be right. It might be I don't see how it is though.
Like 10 times 9 times 8?
Because you're taking 10 permutations 3 at a time?
Yes, because 3 points make a plane.
Maybe. Again, I don't know. I have a hard time with three-dimensional geometry. I really do, to be honest with you. I'm fine on solid geometry, but when they start talking about these lines and points and planes in space, my brain doesn't figure. I'm trying to figure out how you can have more than 10. Well, let me just think about this for a moment. Let's say I start with 2. I'm beginning to see other pictures that might work. I start with 2 points, and I have kind of a deck of cards fanned out. So I have 52 cards. And there's another one going out that direction. You see what I'm drawing, kind of? And let's just assume you have a bunch of planes there. I need more points, don't I? In other words, those 2 points do not define an infinite number of planes. So I've got to have a third point somewhere to make that at least 1 plane. And then I got to have a third point there. I still get 8. In other words, I need 2 for that line, and then I need 8 other points to define 8 other planes. So I still kind of think the answer, no. That actually would, okay, can you see what I'm kind of drawing here? This is a center axis. And these are rectangular planes drawn about its center. So I could draw another one up here. And if I put dots on all those points, I actually am creating another plane. I'm creating that plane and that plane and that plane. And so let's see, if I had 8 planes, then I would have, let's see, in this case, I drew 1, 2, 3, 4, and I created 1, 2, 3, 4 more planes on top and 4 more planes on the bottom. So with my 1, 2, 3, 4, 5, 6 points, I created 1, 2, 3, 4 planes and 4 and 4. So I created 12 planes. We're getting somewhere now. I think you might be right. So you're saying that the answer might be 10 permutate 3, 10 pick 3, which would be 10 times 9 times 8. Does that make more sense to you? 720?
That's usually like the number of, like the answer to these problems. Usually a really big number.
Okay. I can kind of see it because as I tried to draw this figure over here, think of this as kind of a carousel. And I realized that as I made what I thought was an individual plane, I was actually making multiple planes. I was actually making 3 planes. In other words, this little plane at the top here is a plane that I didn't even realize I was creating, but I did with these 3 dots, that dot, and that dot, which each are involved in 2 other planes. And then you have the same thing at the bottom. All of those, no, you don't create a plane at the bottom. Oh no. This problem has me puzzled a little bit, but I'm inclined to agree with you that it wouldn't surprise me if that was the answer. It would surprise me. I just can't picture 720 different planes with only 10 dots, but maybe, since a plane requires 3 dots. I like the question, makes you think. All right. Yeah, I don't know how to make any further progress on that. I don't even know how to look it up. I wonder if Wolfram Alpha would be able to answer that. Probably not, but I may check it out after we're done. Let's talk a little bit about probabilities and combinations. So we know that NPR is equal to n factorial over n minus r factorial. What is NCR? This is where order doesn't matter. In other words, when I was talking about the flush, if you wanted to figure out what's the odds of getting an ace high, well, an ace 8, 7, 6, 5 card flush, the order wouldn't matter. You could get the ace first or you could get the 5 first. The only thing that matters is you end up with those exact same 5 cards. So that would be a combination problem. Do you know what the formula for that is? It's the same as the permutation, only with an extra item in the denominator. And the way I always remember it is when you're done, you got to have 2 n's and 2 r's. So what goes in front of that denominator term? You got to have 2 n's and 2 r's, then this got to be an r factorial.
Oh, yeah, because there's 2 n's and...
That gives you 2 r's and 2 n's. They're all factorials. So if I was to give you, well, let's talk about my flush. 52 cards, combination, 5 at a time. This actually would give you the number of possible 5-card hands you could get from a deck of cards. Okay, in other words, if that was a question, and that's kind of a legitimate question. If you're playing poker, it's a good idea to know, are there 1,000 possible hands or are there 1,000,000? Okay, so what would be 52 choose 5? What is that going to come out to be?
52 factorial over 5 factorial times, what's 52?
47.
47.
Okay. Now, you'll notice that this is going to be, by definition, a smaller number of things than 52 pick 5 would be. Because 52 pick 5 wouldn't be divided by this extra 5 factorial. So this is going to be a much smaller number. But even still, we're going to do it the same way. We're going to cancel from 47 factorial down in the numerator. So my answer is 52 times 51 times 50 times 49 times 48. And the denominator is going to have a 5 times 4 times 3 times 2 in it. That's the 5 factorial. And now you can do things like cancel, and I don't know, you can put that into a calculator. Actually, you can put that into a calculator. Do you have a calculator that does that?
No, I do not.
What kind of calculator do you have?
Just my phone calculator.
There are lots of apps that have scientific calculators on them. I have one on my phone that will do this. Just for the heck of it, let me direct you to a website. In fact, you might have been the one that gave me this website. I don't know. Pretty cool website. After I found it, I didn't know about it. One of my students told me about it, and it's got virtual calculators on there. It's called Desmos. Did you tell me about that or somebody else?
No, but my sister uses it.
Yeah. Notice if I want a scientific calculator, boom, and it does not have the
factorial.
Well, I think, let's see. Yeah, here it is, NPR. Okay, so this was NCR.
Mm-hmm.
I wonder what I'm supposed to put in there. 52 and 5? 52 comma 5 maybe?
I think.
Let's see. Well, let me do a simple one. 6 comma 5, which should be the number 6. Yeah. Okay. So, because that would be 6 factorial over 5 factorial. There is an interesting thing about factorials, incidentally. 1 factorial is equal to what?
1 factorial is equal to 1.
What's 0 factorial equal to?
0?
Nope, also 1. I would love to have a mathematician explain to me how that works, but that is the case. In other words, if you do something like, here, let me give you an example. If I have 3 choose 3, well, what does that mean? It means I have 3 factorial over 3 factorial times 0 factorial, right?
Mm-hmm.
So if the 0 factorial isn't equal to 1, it brings in big problems. And so it is, I don't know if it's defined as a mathematical convenience or what, to be honest with you. But the fact is that 0 factorial is equal to 1. Okay. So let's see what our poker hands was. So it's this one. And it was 52 comma 5. So there are 2,598,000 possible 5-card hands that can be dealt from a 52-card deck that are each different. The same 5 cards in any order, basically. What's this ABC give you? Oh, those are just letters if you need to type them. Okay. Yeah, this is a pretty cool calculator. Here's a good one for you. What do you suppose this number is? Hold on, I did it wrong. This is a really interesting thing. Whoops, gave you the answer first. I didn't mean to do that. I should have asked you what you thought 50 factorial was. You see the answer?
Yeah, it's huge.
That's more molecules than are in the universe. Truly, the number of molecules in the universe is like 10 to the 58th.
Oh.
And you get that number by just multiplying 50 times 49 times 48 all the way down to 1. It's almost inconceivable that it could be that big. Don't you agree? And yet it is. Let's see if it handles. You can make these things cough on some numbers, like 100 factorial growth is about as, that's 10 to the 157th power. Factorial growth is actually bigger than exponential growth. By that, I mean that if you have e to the x, which is exponential growth, divided by x factorial, and what is the limit of that as x goes to infinity? What do you think it is? And it all depends on which one grows faster. In other words, that grows pretty fast, right? You've seen exponential curves. They look like this. That being the growth. Well, guess what? Factorial is faster than exponential, so this one gets a lot bigger than that one as x gets bigger, and this whole thing goes to 0. Whereas if I reversed it and put the x factorial on top, the whole thing would go to infinity. But factorial growth is about as, whenever anybody refers to really high growth, they tend to say exponential. It grows exponentially. They really should say is it grows factorially. If they want to really be dramatic and suggest that the growth is outstanding, they would say it grows factorial. There's a whole section of math where you talk about comparing how things grow, and there's super, super big and other things. But anyway, did you have any specific questions on probability, combinations, and permutations? We've had examples of both permutations and combinations. I've given you examples of both. And how to solve them. And R is always less than N. You can never have an R greater than N.
Because then you go as negatives.
Notice there is one interesting thing about if I say 6 choose 0, or I'm sorry, if I say 6 choose 1, that's the same as this, I believe. Let's see, that's 6 factorial over 5 factorial, no, times 1 factorial. No, that's equal to 6, whereas this would be equal to 1. I think it is 0. Yeah, it is 0. 6 choose 0 is the same number as 6 choose 6. And that becomes pretty important when you start talking about binomial expansion. In other words, 6 choose 0 is going to be 6 factorial over 6 factorial times 0 factorial, right? Which is 1. And this is 1. That's 6 factorial over 6 factorial times 0 factorial. They're both 1. So that's a good thing to know. You probably are more interested in word problems as to how you determine whether order matters or order doesn't matter. Yeah. Although the two problems they gave you, it was pretty clear that order mattered, especially with the 13 sailboats. How many ways can they come in first, second, and third? But notice on the sailboats, we didn't really need to look at it as a permutation problem. We just needed to look at how many ways can you come in first, 13, and then how many boats are left to come in second times 12 times 11. So we could actually do that as a counting problem. That's what I call a counting problem, without knowing anything about NPR. Let me see if I can think of any other wisdoms to give you about probability. Here's one I'll ask you. And I don't know why I always use this one, because this is really a bad one to use. Let's say there's a 50% chance that it's going to rain today, and independently, there's a 50% chance that it's going to rain tomorrow. What's the probability that it won't rain either day? What's probability? Let me make it easier. What's the probability it'll rain both days?
50%.
No, you multiply. In other words, this is day 1. This is day 2. And it's 50% on both days. So if I say what's the probability it's going to rain both days, then both of these have to happen. So it's 1/2 times 1/2.
Oh, 1/4, 25%.
1/4 of the time it'll rain on both days. Now, how would I figure out? Let's make it 60%. We'll make it just a little bit tougher. Now, how do I figure out what's the probability that it won't rain at all?
So that would be 4/10. So 2/5 times 2/5.
Not quite. That would be the probability. Oh no, you're right. Yeah. In other words, if there's a 60% chance of raining, there's a 40% chance of no rain. And since you need no rain on both days, it's 0.4 times 0.4, or 0.16, 16%. Now, the reason this is a bad problem is because a lot of probability problems are based on whether events are independent of one another or not. If I ask you to pull a card from a 52-card deck, and then put it back, shuffle the deck, and pull another card, those are completely independent events. But if I ask you to pull a card from a deck and keep it out, and now pull another card, well, now they're kind of dependent events. And rain is really, technically, in the real world, those are dependent events. In other words, it's very rare where this would be independent from one another. In other words, if it's raining today, it's more likely to rain tomorrow than a random day of the year, just because there's a storm system in the area. So these are never, when you're using rain, it's never independent events. A better thing to use would be flipping a coin. The problem with that is it's always 50-50 for every flip, I wanted to use a number different than 50. I wanted to use 60%. So you would have to do 1 minus 60% to get that.
Yes. Just a little bit harder.
Okay, here's one. You have the letters A, B, C. How many different ways can they be arranged? Set it up as either a permutation or a combination. Does order matter?
Yes.
Then it's a permutation problem. Now, what's my N and what's my R?
Your N would be 3. And then your R would be 3.
Actually, R would be 1. I'm taking one letter at a time, I think. And that gives you 3 factorial over 2 factorial, which is 3, and that isn't the right answer. So I don't have it right. Must be 0. Huh. Because this is such a simple one that I'll give you the answers. It's ABC is one way, ACB is another way, BAC is a third, BCA is a fourth, and finally we'll do the C's, CAB and CBA. That's the only 6 ways that you can arrange those 3 letters with order mattering. So the answer is really just 3 factorial. I'm not sure that it's 3 things chosen 0 at a time. I don't like this. I'm not sure how you come up with 6. I know 6 is the right answer, and you can always, if there's small enough number of combinations or permutations, you can usually count it out. The hard ones are where they give you so many. In other words, if I said how many different ways can you arrange 26 letters in the alphabet, I wouldn't be able to do it this way. I wouldn't have enough time. So I'd have to do it as a NPR problem. The only thing is I can't figure out how to apply that to here.
Well, I know you get it by 3 times 2 times 1.
Right. So you can definitely get it that way. Question is, and order matters, so it should be a permutation problem. I think you got to have a 3 on the left side. Question is, the only number on the right side that gives you 6 is not 1. In other words, I could kind of see taking 3 letters one at a time. 3 letters taken 3 at a time gives you 3 factorial over 0 factorial, which is 6. That's what it is. If I add a letter, then it's 4 letters taken 4 at a time, and that's going to be 12. So when you have a problem like that, that's the way to do it. It's not quite as easy to understand, because when there's only 3 letters there, it's 3 letters taken 3 at a time, I guess. Yeah, you are taking 3 at a time. Each answer has 3 letters. I guess that's how you translate that, the word problem to the... That's the biggest difficulty, is taking a word probability problem and converting it to the proper NPR or NCR. Joseph, I forgot I have a 5 o'clock, so I'm going to have to go run on you. But good luck. I think you're in good shape. Have a good Christmas, and I'll talk to you probably next semester.
Okay, thank you.
Get an A on that test.
I will.
Otherwise, your mother's going to be mad at me.
Yeah, and she's probably going to kill me.
She'd be madder at you than me, huh? Okay.
Yeah.
Do well. You will.
Okay.
You know this stuff.
Thank you.
All right. Bye-bye.
Yep. Bye.